Welcome to the solid phase peptide synthesis series made by Dr. Naomi Lee's research group at Northern Arizona University. In this video, we will describe how to cleave your peptide from the resin and the side chain protecting groups. Once you have completed the coupling and deprotecting of your final amino acid and optionally capped the N terminus, your peptide will look something like this. Each of your amino acid side chains has a protecting group, shown in red, that needs to be removed, and your C terminus is still attached to your resin. If you recall from the resin preparation video, your resin linker actually looks like this. The cleavage reaction works to deprotect your amino acids and cleave your peptide from the resin in one step. The reagents we use in cleaving are trifluoroacetic acid, otherwise known as TFA, triisopropylsilane, otherwise known as TIPS, and water. Both the resin linker and amino acid protecting groups are acid labile and are removed by TFA, which is a strong acid. TIPS acts as a scavenger to collect cations produced during this reaction. Water acts as a proton donor and acceptor to help mediate the reaction. Let's take a closer look at how these reagents remove protecting groups and cleave the peptide from the resin. Using the example of a Bach protecting group on lysine, deprotection begins by TFA protonating the ester in Bach. This causes a tert-butyl cation to leave and an unstable acid to form. The TFA deprotonates the acid, which triggers a decarboxylation that results in our deprotected side chain and a carbon dioxide side product. In the case of lysine, the amine side chain can be protonated by TFA or water after deprotection. This process works similarly for protecting groups on other amino acids. TIPS is used as a scavenger that collects cation side products, like the tert-butyl in this example. Without a scavenger like TIPS, these cations can react with the side chains of amino acids and form undesired side products. TFA cleaves the resin from the linker at multiple sites, which causes several cations to form. These cations are similarly neutralized by TIPS. You'll notice that the cleavage step results in the amidation on the C terminus, where instead of a carboxylic acid at the terminus, there is an amide. If this is not what you want, you can use a preloaded amino acid resin so that your C terminus will not be amidated upon cleaving. We use the cleaving reagents in an 18:1:1 ratio. At a scale of 0.01 millimoles, this ratio results in a cleavage cocktail of 3 milliliters of TFA, 0.16 milliliters of TIPS, and 0.16 milliliters of water. This should cleave an entire peptide at the 0.01 millimolar scale. We can also do what we call a microcleavage, where we take a small portion of uncleaved resin and cleave it on a smaller scale. This allows us to analyze the sample via mass spec and chromatography without cleaving the whole sample. Let's first look at how to perform a full 0.01 millimole scale cleavage. Before the cleaving step, make sure that your peptide has been washed of any residual reagents with DMF, then extensively washed with TCM to dry the resin. This is important as any residual DMF can inhibit the reactivity of TFA. Once your resin is dry, create a cocktail of TFA, TIPS, and water, and quickly add this to the reaction vessel. TFA is a very strong corrosive acid, and even small droplets can cause damage to your skin and eyes. You will need to wear gloves and a lab coat when using this chemical, and always use it in the fume hood. Allow the vessel to rotate for 1 to 1.5 hours. At this point, your peptide should be cleaved and deprotected in solution, which is what you will need to collect. Therefore, it is incredibly important that you drain your reaction vessel into a clean flask. If you drain the solution into a waste vessel, your peptide will be lost. You can now discard the vessel, which only contains cleaved resin. Transfer your peptide solution into a round bottom flask and rotovap off as much of the TFA as possible. Refer to our video on how to use the rotovap for more guidance on operating this instrument. TFA has a very low boiling point, and the majority will evaporate off quickly, but some will still remain. Because TFA is such a strong acid and can cause degradation to our peptide over time, we will need to perform an ether precipitation to fully remove the TFA from our peptide. To perform a microcleavage, remove a small amount of dried, uncleaved resin and place it in a microcentrifuge tube. Add a cleavage cocktail of 375 microliters of TFA, 20 microliters of TIPS, and 20 microliters of water, and let the tube rotate for 1 to 1.5 hours. Once the reaction is complete, you will need to use the air hose to help evaporate the TFA. Be extremely careful during this process, as the solution can easily fly out. Once the majority of the TFA is evaporated, add a 50-50 water acetonitrile solution to the tube to prepare it for the MALDI and HPLC analysis. Typically, 100 microliters to 150 microliters of the 50-50 solution is enough for both analyses.